Okay, this is actually Adamson-Edwards 4.5.4 theory. So this is for inferential statistics. So finally, when it comes to a researcher analysing their quantitative research, sorry, oh, what? Sorry. Okay. When it comes to research analysing the quantitative research, the last stage that needs to be carried out is known as inferential statistics. This acts as a way for the researcher to make further interpretations from their data through the use of inferring to eventually draw conclusions. In order to infer, a researcher must use the technique of constructing a hypothesis. A hypothesis can be constructed into one of three different formats. Firstly, we have the null hypothesis. This is the type that everyone starts with, as it represents a hypothesis that suggests that nothing will happen to the data and that nothing new has come about, therefore allowing the researcher to not make any extreme assumptions about their research that may be completely biased or irrelevant. Following on from this, if the researcher then starts to find that they have a slight hunch towards the research, then they might make an alternative hypothesis that is made up of two different segments. Firstly, if this alternative hypothesis that is a researcher is suggesting refers to the research taking no specific direction, this is referred to as a non-directional hypothesis. This is because the particular suggestion regarding the data that they're making wouldn't refer to a particular area of research being affected, therefore indicating that they think that there will be a change in results, but don't know in what way. However, a researcher may find that they start to recognise some kind of pattern or significance in a specific region of data, consequently making a one-directional hypothesis, otherwise known as one-tailed. This kind of suggests that the researcher is making an assumption that perhaps their research will change in a certain way. For example, a study looking into the certain variable affecting the certain reach results of British gymnasts maybe make a one-tailed hypothesis that the certain reach scores will increase. This can be regarded as a one-tailed hypothesis, as it making specific suggestion about the results. Another key aspect of inferential statistics is the statistical significance. A statistical significance refers to a researcher setting a particular value prior to a research that would indicate a level of significance. However, so that a researcher can test the level of significance that their data has provided, they must go through the process of determining what to use. This is done by firstly deciding whether their data fits into one of three categories. These are nominal, interval ratio, and ordinal. If a piece of data was ordinal, it means that there has been categorized previously, and therefore it would be suggested that it consists of differences among frequency counts. Different frequency counts. As a result of this, the chi-square test is normally commonly used, as it is well suited for testing the relationship between categorical variables, whereas a research data consisting of interval or ratio data can lead to one of the three tests. Firstly, the researcher should establish whether they are looking for a relationship to analyse the mean differences or the mean differences within their findings. For instance, if their data consisted of two or more variables, then it's likely that they were researching a relationship and therefore would be best suited for the Pearson's product test. This test suits a relationship between interval and ratio data due to its characteristic of developing a strong or weak association between the different variables, whereas the researcher may be trying to test the difference between their values and therefore would use the independent t-test or the dependent t-test. This will be decided by if the data consists of two separate groups of data, independent t-test, or two related groups of data, which would fall under the dependent t-test. Finally, researchers may be categorized as ordinal data. This regards as a quantitative study that's been ordered in a particular way, like being ranked. Much like the other branches of characteristics for choosing an appropriate test, the ordinal data is split up into another three branches of determination. Firstly, if the data shows a relationship between rankings, then the Spearman test would be best suited, whereas if there are evidently differences between rankings of two or more groups, then the Mann-Whitney test should be used. And finally, if the data possesses differences between related rankings, then the Wixon matched pairs sign ranks test is most commonly used. Finally, inferential statistics consists of one or more aspects. This is whether or not a researcher is using a parametric test or non-parametric test. A parametric test refers to data that has been normally distributed across a particular study. This is usually used for the data that is continuous, like an interval or ratio data. The kind of test requires a much larger sample of size and also for the data to come from random sampling. The parametric test is regarded as more powerful than the non-parametric test due to the fact that they are widely regarded as more likely to indicate a true difference of relationship within a quantitative study. However, on the other hand, a non-parametric test involves the researcher not making any assumptions about the distribution of data that has occurred. These tests are commonly used for small sample sizes that it struggles to analyse normally. Unlike the parametric test, the non-parametric test uses the data that isn't randomly sampled and is usually established as being involved with ranks and ordering as opposed to real data, therefore suggesting that it isn't as powerful as its counter test. Moving on to testing for the relationship. So, on the other hand, a researcher may come to the conclusion that they need to test for a relationship amongst their findings. Therefore, it can be suggested that a correlation needs to be found for a particular quantitative test. A correlation acts as the degree of association or relationship between two or more different variables. This correlation that is then found can be determined as either positive or negative. However, unlike other aspects among analysing quantitative data, a correlation isn't determined by a line or prediction of causality. This is because it doesn't matter what axis the variable is regarding. Examples of the variation correlation terms include strong, weak, moderate, and non-existent. Whereas a correlation can also be positive or negative. For example, in Figure 17, we can see two examples of different correlations, or three examples of different correlations, regarding the relationship between British gymnast static sprint results centimetres and vertical jump scores in seconds. If there was a positive correlation between these two variables, then their scatter plot graph would be like the graph on the left. Whereas if there was a weak negative correlation between these scores, then it would look like the graph in the middle of the slide. This would be due to the fact that one of the variables would be having a negative effect on the other, and therefore made each other decrease in terms of what is being measured. However, finally, on the right-hand side is an example of weak correlation, which could be shown if the vertical jump and static sprint results didn't associate with each other. In this case, we could make the assumption that there would be a positive correlation, as British gymnasts, as in order to have a strong vertical jump score, you need strong and fast muscles with twitch fibers, which is also needed for a strong static sprint result, and vice versa. However, this is only an assumption. Moving on now to the decision tree. In order to investigate the relationship correlation between two sets of data, a researcher would use a particular decision tree like the difference statistic to decide on what is to use. Firstly, if both the variables within a study are dependent and therefore both aren't being controlled by the IV, then the researcher would take the next stage making the assumptions about the data population. This means that if no assumption is made by the researcher regarding the data's population sharing characteristics, then they would use a Spearman's rank test. This is because the particular test would then assess the degree of association between these two variables that can be described. Whereas if a researcher made an assumption about the population of the findings, then this would use the Pearson's product moment correlation coefficient test. This is because the Pearson test can now test the strength of this relationship that has been suggested. However, if a study presents an independent variable that causes a change to the DV in a study, the researcher will have to take a different route. This will consist of them using a linear regression analysis due to the fact that they have an appropriate and apparent population that can be assumed. The first test for testing for the relationship that we're going to cover is the Pearson's product moment correlation coefficient test. This acts as a parametric test for correlation within data. Therefore, it would be assumed that it's used when it is suggested that normal distribution has occurred. This involves two sets of paired data from the same group of research participants. So, for example, here I've used the data from a group of British gymnasts regarding the bicep and tricep skin fold caliper measurements. In order to use this test, I'd have to work out a series of calculations due to the complex nature that it possesses. This involves a calculation such as squaring the data that I have regarding bicep and tricep skin fold caliper measurements. All the calculations that a researcher would be forced to work out have been completed on this slide. These calculations can then be used in order to fill in the equation for the test, which is proposed in the top of the slide. Positioned at the top of the slide. Once I had completed this test, I managed to get a calculated R value. This came out at 0.47781.087 and can now be used in order to try and determine the degree that the fact the test would lack validity if it was comparing the relationship between two different sets of participants. These two sets may possess different properties to the British gymnast and therefore wouldn't be relevant to the data. Following from this, now that we have the R value, we can now compare this to the critical values table. This is done by firstly working out the difference, the DF, which in this case is n minus 2, which is 8 minus 2, which equals 6. The DF can then be used to help us understand which row to look across to finding our critical value in terms of association within this study. The p-value that we use, however, is previously set, and and we use it for a two-tailed hypothesis. So if the if the R value that we calculate is lower than the R p-value of 0.05 that I've circled on the graph, then there is a significant relationship. However, if it's higher than that, then there is not. As we can see, the critical value is larger than the calculated R value. Therefore, there isn't a significant relationship or correlation between this data. Therefore, we would accept the null and reject the two-tailed hypothesis that something will change within the data. Following from this, we have the Spearman rank order test. Unlike the Pearson's test, this test has a non-parametric test for the correlation within a data set. This is because they're part of a study where the data hasn't been assumed, and therefore, according to our decision tree, would bring us to the conclusion that the Spearman rank order test should be used. Once again, it must be the same participants so that it's fair and relevant to each other, therefore eradicating the chance that two completely different pieces of data are being tested for an association. The equation for this test can be found at the top of the slide. However, once again, in order to complete this test, researchers have to make a series of prior calculations regarding their data set. For example, a study looking into the relationship between British gymnasts standing vertical jump and thigh graph results may choose to use this test. As a result, they would complete the calculations labelled on the slide as figure 19. These results can now be applied to the equation for this test, so that a calculated R value can be determined. This R value can then be used to work out a correlation coefficient between the data. As a result of this, the calculated R value for the specific study comes out at 0.2844848. Therefore, much like the other tests for correlation, we can now use the critical values table in order to come to the conclusion on our findings. In this case, the DF calculation comes out as 8 after completing the calculation of number of participants, take away 2. This allows us to look across the 8th row and down the 0.5 p-value column, as this is our level of significance, therefore leaving us at the critical value of 0.74, which is bigger than our calculated p-value. Consequently, meaning that there once again no significant relationship between the two sets of data within the same group, and therefore we must reject the two-tailed hypothesis and accept the null, and therefore nothing changed. I'm going to end the video on this part.